In a closed system, all the energy that starts in the system stays in it for all of time. So this energy could be converted from potential energy to kinetic energy, or the other way around, but it stays in the system. And what type of energy it is often reliant on the distance between particles, the speed they're moving at, their positions, and so on. So in problem 10 of the AP exam, we have particle A and particle B, each of mass m, move along the x-axis, exerting a force on each other. The potential energy of the system of two particles associated with the force is given by the equation U equals beta over r squared, where r is the distance between the two particles and beta is a positive constant. At time t equals 0, particle A is located at x equals 2d, with an initial speed of v0 to the left. Particle B is at rest at the origin as shown in the figure above. And this is the figure that it is referring to. So question 10 of the AP exam asks us, which of the following equations could be used to find r min, the minimum distance between the masses, as particle A approaches particle B? So to do this, we want to find the initial energy of this inside this system, and then from there we'll set it equal to this final energy where we have r min. So we can say that the initial energy, let's consider the potential energy we have. So the equation which gives us the potential energy is U equals beta over r squared. And in this case, r is 2d, because that's the distance between the two particles. So at time 0, U equals beta over 2d squared, which is going to be 4d squared. So that's our potential energy. What about our kinetic energy? So the kinetic energy is 1/2 mv squared, right? And we know that our particles' masses and velocities. So particle A is moving at a velocity of v0, right? So we can say that that would be 1/2 mv0 squared. And particle B, we don't really have to consider, just because it's stationary, so v is 0, so that makes this whole expression 0. So this is going to be our initial energy. And because this is our initial energy and it's a closed system, this is going to be our energy for the whole duration of whatever is going on in this situation. So we want to find the minimum energy, right? So the way this equation works is that we want the radius to be at a minimum. So as the radius gets larger, we know that this expression for, as the radius gets smaller, we know that the potential energy gets larger. So where there will be the maximum potential energy, there will be the minimum kinetic energy. So what we have is, so with no kinetic energy, there's only potential energy. So we take the expression for potential energy and just put our min there. like this. And there's no need to change the format of this and isolate our min, because this is one of the options on our test. It is option number D.